we're going to have to use the periodic table for the molar mass here. I know I didn't really talk about that in detail yet, but hopefully you guys remember that from the previous classes. But here we're going to get started with our starting value, which is 4.12 times 10 to the 24. And it tells us that it's Fe atoms, okay? And then we are looking for mass. So typically, when we're talking about mass in this class, what unit of measurement are we looking for?
Grams.
Yeah, grams. Okay, so we want to turn atoms into grams. All right, so from there, we just set up a quick fraction. We want to get rid of atoms, but before we can turn it into grams, we want to turn it into moles. Okay, so we can use our conversion factor from last time, Avogadro's number. So 6.022 times 10 to the 23rd, and that's going to be atoms. And so we set up this fraction to get rid of the atoms. All right. So that's what we learned last time. Okay, so we're not done though, because we need to turn moles into grams now. So in order to do this, we need to use the atomic mass, or we can just call it the molar mass. And that's the number on the bottom of the box in the periodic table. So we're going to take a look at iron. And if we take a look at iron on the periodic table, we can see that its molar mass is going to be 55.84. So we're going to set up another fraction. And then it'll be 1 mole of iron is equal to 55.84 grams of iron. Okay. So we just need to plug that into our calculators, and that's going to give us our final answer. So that's how we can turn atoms into moles, and then turn it into something that makes a little more sense for us, which is grams. Okay. Any questions on that setup? Okay. I'll give you guys about a minute to plug that into your calculators, because I do want to give you some time to prep or to practice using your calculators. And then after that, we'll see if you guys got the right answer, and then we'll go over to that. Okay, so punch that into your calculators. Let's see what you guys get, and then we'll move on. Okay, so you guys plug this into your calculator. I'm not going to go over the work, but hopefully you guys get 382.1 grams of iron, something like that. Everybody got something close to that?
Yep.
Yep. Okay. Just making sure. If you guys have any questions, please let me know. Yes.
Does it seem like unit 1 for balancing?
Yeah, it is. It's gonna get a. We're gonna do stoichiometry next, which is basically dimensional analysis, just a special type. Yeah, good point. Okay, let's move on to the next thing. Empirical formulas. Now, I know this looks very, very complicated, right? There's a long paragraph and there's this little graph thing, right? But I'm going to tell you guys just how to find empirical formulas very easy, okay? We learned last time that empirical formulas tell you the relative number of atoms in a molecule, right? So like the ratio. So if you guys remember way up here, oh, maybe not in this unit, but in the previous unit, do you guys remember how we talked about how you can basically simplify a molecule, right? If you had something like H2O2, hydrogen peroxide, this is the molecular formula, but the empirical formula, we just look for the simplest form of this, which will be HO. You guys remember that? The empirical formula? Okay. So now what we're going to do is we're going to learn how to find the empirical formula using percentages. Okay, so there's this thing right here, but I think it's just easier if I show you how to do a problem. So we're going to go into 3.9. And just a heads up, AP Test loves empirical formulas. So just make sure you're comfortable working with them, okay? So 3.9, it says determine the empirical formula with a compound that is 81.32% carbon, 5.12% hydrogen, and 13.56% oxygen by mass. So it gives you the percentages of all the elements inside the compound, right? So what we want to do first is make sure you guys write this down, because I think this is the easiest way to solve these empirical formula problems. You're going to assume, okay, you're going to assume that the compound is 100 grams. And I'll tell you guys why in just a second, but make sure you write this down. You're going to assume that the compound you're looking for is 100 grams. Okay, now the reason why we want to assume the compound is 100 grams is because it makes the percentages really easy to work with, okay? So let's say that our compound right here that we're looking at is 100 grams. If it's 81.32% carbon, what's the mass of carbon inside the compound? 81.32, so in the compound. So if the compound is 100 grams and it's 81.32% carbon, that means we can assume, hey, there's 81.32 grams of carbon inside of this compound. Does that make sense? And that's why we assume the compound is 100 grams. Just makes it really easy to work with the percentages. So it's 5.12% hydrogen. So what's the mass of hydrogen inside the compound? Yeah, 5.12 grams. And then lastly, it is 13.56 grams of oxygen. And so that's why we assume that it's 100 grams for the entire compound, because the entire thing is 100%. If it's just 100 grams, we can just take the percentages and turn it into grams. Okay. All right, so what we're gonna do now is we're gonna turn the grams into moles, because if we turn it into moles, we can put it into the molecular or the empirical formula. So I'll do the first one with you guys, and then I'll have you guys try the other ones on your own. So super simple. We got carbon. Okay. We take a look at carbon on the periodic table. What's the molar mass of carbon? Yeah, 12.01 or just 12 is fine. Okay, so we're gonna do 12. So that's how we can turn the carbon. So 12 grams per 1 mole of carbon. That's how we can turn it into moles of carbon. So what we want to do is we basically just want to turn all the grams into moles. So I'll give you guys about 2 minutes. You can split it with the person next to you. But I want you guys to find the moles of carbon, moles of hydrogen, and moles of oxygen inside of this compound. And then I'll show you guys how to finish up the rest of the problem. Okay, so take about 2 minutes to try that. All right, so basically you just need to divide by the molar mass and that'll turn grams to moles. Okay. All right, so you get these values for the moles. Now what we're gonna do is we're gonna write a chemical equation, or not, sorry, chemical formula using these values for moles. So we're gonna write that this compound right here is going to be 6.78 moles of carbon. We're gonna write that it is 5.12 moles of hydrogen. And then it's going to be 0.85 moles of oxygen. Now I know this looks really weird because we never put decimals in the molecular formula because it doesn't make sense, right? But we're doing it just kind of as a way to just start the formula, and then we're gonna be cleaning it up to make it look like a actual molecular formula. Okay. We'll just jot that down real quick. Okay, so like we said, empirical formulas are just ratios of how many atoms there are relative to other atoms inside the molecule. So what we're gonna do is all we gotta do is on our calculator, we just need to divide all of these numbers by the smallest number that we have. So which one of these three is the smallest number? Yeah, 0.85 for oxygen, right? So we're gonna divide 6.78 by 0.85. So I want you guys to punch that in your calculator, see what you guys get. 6.78 divided by 0.85. Okay, you should get about 7.97. Everybody get around there? Now, what whole number is that really, really close to?
8.
8. So we can just round that to 8. Okay. Now we can move on to the hydrogen. We're going to go to 5.12 divided by, divided by 0.85. And that's going to give you 6.02. Now, what whole number is that really close to? Yeah, just 6. So H6. And then we don't even need to do the oxygen one. 0.85 divided by itself is going to be 1. So there you go. That is our empirical formula. So that is how you can find the empirical formula for a compound just by knowing the percentage of each element inside of it. Okay. So there's a couple things, I guess. It's first assume a 100-gram compound. You turn the percents into grams. You turn them into moles. And then you just do this last step. Okay. Make sense? Hopefully not too bad. I do want to point out again that AP Test loves working with empirical formulas. So just be very comfortable working with this. We're gonna actually apply it inside of like our regular content later in the year. So we won't see it for a little bit after this unit. But just be comfortable finding empirical formula, okay? All right, you guys think you could try one on your own? Okay, beginning to end. All right, so I'm gonna leave this up here just so you guys have a reference. But I want you guys to do 3.10 on your own. So just make sure you pull it up on Canvas if you don't already. You're gonna be finding the empirical formula for vitamin C, ascorbic acid. You got the percentages right there. Again, same process. I will give you a heads up that this last step right here is gonna be a little bit trickier. Because the numbers won't be as clean. I know that right here we had like 7.97, so it was really easy to turn it to 8. This one was 6.02, so it was really easy to turn to 6. For this one, the last step, the numbers are gonna be a little bit uglier, so it'll be a little harder to round. You're gonna have to finesse the math a little bit more, but I believe you guys can do it. So just a heads up, and then we'll go over it in about 5 minutes. Okay, so take about 5 minutes to try out 3.10. And then just make sure you watch out for that last step, all right? All right, so again, just make sure you turn the percentages into grams. And then we're gonna assume 100 grams. And then what we're gonna do is just turn it into moles by dividing it by the molar mass. Okay. So far, so good? All right. So the next step, like I said, is gonna be the part that's a little bit funky for this one. And the reason why is because it's gonna be carbon 3.41. Hydrogen is going to be 4.58, and then for oxygen, it's going to be 3.41. So for this one, it might seem really simple, right? It's like obviously divide by 3.41. Okay, so if we do that for carbon, we're just going to get C1, and oxygen, we're going to get O1. Okay, now the part that gets kind of weird is going to be with the hydrogen. So if we take a look at hydrogen, we're going to get 4.58, and we're going to divide it by 3.41. That's going to give us about 1.34, okay? So 1.34. And the problem here is, if you notice, 1.3 isn't really close to 1 or 2, right? It's kind of in the middle. And so we can't round this down to 1, and we can't round it up to 2. So we're in a weird situation where this number right here is not next to a whole number. And so we got to start working with the numbers in order to get it close to a whole number. Okay. So what we can do is, this is the method I usually use, is I just kind of try to multiply the numbers and see if I can get it close to a whole number. Okay. So what we can do is we can take the 1.34. So 1.34, and I just multiply it by 2. Okay. Is that close to a whole number?
Yeah.
Not really, right? So that's probably not the best one. So just keep going up, multiply by 3. Now, is that close to a whole number?
Yeah.
Yes. So that's very close to 4. So that's going to work. So what we're going to do is we're going to take this entire formula, multiply it by 3, because if we do that, we get C3, H 4.02, which is very close to 4. So H4 and O3. And that's how you can make an ugly molecular formula or empirical formula into something nice and clean like that. Okay. Yes.
What about when it gets really granular, like with the 7 to like 20 to the 30s?
Yeah, that means for the AP test, you're probably going too high. Yeah, they're gonna try to keep it as nice and clean like this as possible.
Okay.
Yeah.
What if you're like the actual chemist?
You're an actual chemist. There are other tricks you can use. But that's beyond the scope of this class. Yeah. He's an actual chemist. All right, make sense, guys? Okay, so that's empirical formulas. Now what we're gonna do is we're gonna be talking about how to turn this into a molecular formula. Okay, so that's the next step. Okay, so what we're gonna do is I want you guys to copy down this formula right here. But basically, once you have the empirical formula of something and you have the molecular weight, you can just use this equation in order to find the molecular formula. Okay, so I'll explain what that means, what that looks like in a second, but just copy down that formula right there, and I'll show you guys how to use it. All right, so let's take a look at 311. So 311, it gives us the empirical formula. It tells us this chemical, mescaline, okay, has an empirical formula of C3H4. So I'm going to write down C3H4, and this is the empirical formula, okay? And then it tells you that it has a molecular weight. So the weight of the real molecule, mescaline, has a molecular weight of 121 AMU, okay? So it gives you the empirical, and then it gives you the weight of the real thing. So what we can do is we can use this formula right here in order to find the whole number multiple. Okay, so first it tells us to put the molecular weight on top of the fraction. So what's the molecular weight of this compound? Yeah, it's given to us, right? 121. So we're going to put 121. Let me put it on this so it looks a little easier. So 121 divided by the empirical formula weight. So what we're going to do is we're going to have to find the molecular weight of the empirical formula. Okay, so I'll do that with you guys. Carbon is 12, right? So if there's 3 carbons, what's the molecular weight of just the carbons? 36, yeah. So 12 times 3. Yeah, 12 times 3. Hydrogen is just 1, and there's 4, so that's 4. So all the hydrogen are 4. So the empirical formula weight is 40 AMU. Okay, and that's what we mean by finding the empirical formula weight. So I'll pause right there, but any questions on why we plugged in those values? Hopefully it's not too bad. All right, so just to kind of summarize again, basically we took the molecular weight, which is given to us, 121, we put it on top of the fraction, divided by 40, which is the empirical formula weight, which is just find the weight using the empirical formula. And then we just need to divide it to get the whole number multiples. So 121 divided by 40 is going to be about 3, okay? So 121 divided by 40 is 3.025, which is very close to 3, right? And so again, we want it whole number, so this is going to be about 3. So in order to find the molecular formula, the real formula, all we have to do is take this guy right here and multiply it by 3. Okay. So if we multiply the carbons by 3, how many carbons are there? 9. How many hydrogens? That's it. That's the molecular formula. Okay. And if you want to double check your work, you can find the molecular weight of this, and then it should get 120. All right, so that's how to find empirical or molecular out of empirical. All right, guys, so I'll pause right there to ask you guys a quick question. Do you guys want to do one more practice question with the empirical, or do you want to just move on to stoichiometry? Who wants to do one more practice? Okay, that's majority. Let's do one more practice, okay? So let's do 3.12. This is kind of combining what we learned today. So part A is going to be using the percentages to find the empirical formula. And then part B is doing what we just learned about to find the molecular. Okay, so I'll give you guys about 5 minutes to work on this again. You can work on it with the person next to you, and then we will go over together. Okay, so I set up the grams to moles right here, and so you should get an unfinished or empirical formula that looks like this. So pretty obvious that you're gonna divide everything by 3 point, oh, sorry, ooh. Divide everything by 3.23, and you should get basically 3 for the hydrogen. Okay, so divide everything by 3.23, and you should get an empirical formula of CH3O. Okay, so that's your empirical formula, and that's gonna be the answer to part A. Okay. Any questions about that one? Hopefully that's not too bad. So we've been practicing. All right, now the new thing we just learned was finding the molecular formula. Now it tells you right here that the molar mass is 62.1 grams per mole. Another way of talking about grams per mole is AMU, right? And so that means that the real formula, the real molecular formula is going to have a molar mass of 62.1 grams per mole. So what we're going to do is basically just use the formula that we just learned about. So first thing we got to do is find the molar mass of this thing right here, the empirical formula. So carbon is 12, hydrogen is 1 each, so plus 3, plus your oxygen, which is 16. So you should get a molar mass for the empirical formula of 31 grams per mole. Okay. So far, so good? Okay. All right, so what we're going to do is we're going to plug it into that formula we just talked about. We're going to take the real molar mass, 62.1. We're going to take the empirical formula molar mass, which is 31. And that's going to give you an answer of basically 2. Okay. So from there, we're just going to multiply the empirical formula by 2. That's going to give you C2H6O2. And that will be your molecular formula. So this is the formula of the real compound of ethylene glycol, which is used in antifreeze. And this is the empirical formula. This is the ratio. All right. So that's pretty much the extent of empirical formulas. If you're comfortable doing this, empirical formula should be kind of a breeze for you basically for the entire year. It's not going to get much harder than this one right here. All right. Okay. Any questions on how to solve any part of it? All right, now before I close up the class, I do want to just talk very briefly about stoichiometry. We're actually not going to finish a problem. I just kind of want to give you the intro information because you guys do have homework and everybody does the reading, right? Yeah. Everyone always tells me they do the reading every year, but I know nobody does the reading. But anyway, just so you guys have some intro information before you guys do the reading and your homework. Let's talk about very briefly what stoichiometry is, and then I'll close up shop. We're not going to do the first problem, okay? But let's talk about what stoich actually means, okay? So I know there's different like graphs and stuff like this that tell you what stoichiometry is, but you can kind of think of stoichiometry as like a way to use a recipe, okay? So I'm going to do a little illustration since we are just talking about meth. Okay, let's talk about making meth, okay?
Yeah.
So meth has a lot of, let's say, for example, meth has a lot of steps to make it, but let's just say it's one step, okay? And it requires a bunch of ingredients. So we'll do meth ingredient number 1 plus meth ingredient number 2. And let's just say it just takes 3 ingredients to make meth, and then that makes your meth, okay? So this right here is going to be your chemical formula. Okay, so this is your chemical formula. Now, let's say that in order to make meth, you need 2 of these and 3 of these, okay? Stoichiometry is basically figuring out if I want to make, let's say you want to make a lot of money. So let's just say I want to make 1,000 grams of meth, okay? If I want to make 1,000 grams of meth, it's basically using the chemical formulas to figure out, hey, how many grams of meth ingredient number 1 do I need to get at Home Depot, right? How many grams of ingredient number 2 do I need to get from CVS? And how many grams of this do I need to get from Mr. O? I'm just kidding. But yeah, so that's basically what stoichiometry is. It's if I want to make 1,000 grams of meth, how many grams of everything do I need in order to make my desired result? So it's basically making a shopping list before you go and cook. Okay, I could have used a better example, like, making food at home, but that's kind of boring. But basically that's what stoichiometry is. We're using the chemical equation right there at the top to figure out how many grams of each ingredient you need in order to make your desired result. So hopefully that helps you understand stoichiometry a little bit better. Please don't tell your parents that I'm encouraging to make meth. I never encourage any drug use or substance abuse. It's a controlled ones or Schedule 1 controlled substance. Please don't make it. But yeah, that's pretty much it. We'll start stoichiometry as soon as we come back to class on Wednesday.